So in chapter 13, we're going to talk about vector functions. This object is vector functions. So after we talk about these new types of functions, we're going to learn how to do calculus on these types of functions. So let's start by writing the definition. Definition. A vector valued function is a function that has some components. Those components are scalar functions. A vector valued function or just vector function is a function with components. These components are all scalar functions. So we usually denote a vector function this way. We say that we have, for example, f of t equals to, so since it's a vector function, we use vector symbol with some components. Those components are all functions. So suppose you have f of t, comma, g of t, comma, h of t. Instead of f of t, we can use r of t as well. But note that since it's a vector function, we usually write a little bar on top of r, or if you don't want to use bar, you need to bold this letter. R of t equals to, this is a vector function. It means that it has some components. These components, instead of being numbers, are functions. For example, our function r of t, or if you want to use bar, that's absolutely fine. Bolded letter or the letter with bar on top of it equals to, so the components for this function, t cubed, comma, ln of 3 minus t, comma, square root of t. This is a vector function, and the components of this function are scalar functions. T cubed, ln of 3 minus t, and square root of t. These are the components of the function. Very well. Now that we have a function, we can talk about the domain of the function, and we can talk about more calculus characteristic of these types of functions, like how do we find the limit of these types of functions. So let r of t be equals to f of t, g of t, and h of t. be a vector function. The limit of this function, the limit of this vector function, as t approaches to, like a number, is equal to, so what do? We take the limit of each of these components. So we have the limit of f of t, limit of g of t, and limit of h of t while t approaches a. Limit of f of t while t approaches a, comma, limit of g of t while t approaches a, comma, limit of h of t while t approaches a. So this limit exists if the limit of each of these components exists as well. Each of the limits of the component exists as well. Let us go over one example together. Example. So suppose you have this function. This vector function is defined this way: 1 plus t cubed, comma, t e to minus t, and comma, sine t divided by t. And question says, hey, find the limits of this vector function rt while t goes to 0. There you go. So to find the limit of this vector function, we have to take the limit of each of these components. The limit of 1 plus t cubed while t goes to 0, comma, the limit of t e to minus t while t goes to 0, and the limit of sine t divided by t while t goes to 0. So we are getting back to elementary calculus. This is just a polynomial function. To find the limit, we just use substitution. This is equal to 1 plus 0 to the third, the limit of t e to negative t. First, you need to write it as t divided by e to the t, then send t to 0. And here you have, if you plug in 0, here you get 0 divided by 0. By using L'Hopital's rule, you can just write it as cosine t divided by 1, and then take the limit while t goes to 0. So this is equal to 1. This is 0 divided by 1. And this is just cosine of 0, which is 1, 1 divided by 1. So the limit of this vector function is 1, 0, and 1. Perfect. Remember continuity. We say that a function is continuous if the limit of the function is equal to the value of the function at the given point. A function like r of t is continuous at t equals to a if the limit of your function while t approaches a is the same as the value of the function after plugging a. Well, when we have continuous components, then we can talk about the graph associated to those components. Definition. Suppose f of t, g of t, and h of t, all those components are continuous on an interval like I. Then C, or the set of all points x, y, z, such that x is equal to f of t, y equals to g of t, and z equals to h of t, t belongs to I, is called space curve. Let's go over one example. This example says, describe this space curve. C, which is equal to the set of points x, y, z, such that x is 1 plus t, y is 2 plus 5t, and z equals to minus 1 plus 6, or equivalently, we can write it this way. Describe the curve. Defined by a vector function RT equals to 1 plus t, this is the x component, 2 plus 5t, the y component, and negative 1 plus 6t, the z component. Recall that in previous chapter, we start talking about points. Then we talked about lines. Then we talked about planes. Then we talked about surfaces. Points, just points. What's the equation of a line? Parametric equation of line is defined this way. X equals to x sub 0 plus 80, y equals to y sub 0 plus bt, and z is equal to z sub 0 plus ct. Well, as you can see, x, y, and z, they are very similar to parametric equation of lines. So this vector function represents a line in the space. So here you have one line. This line passes through the point p sub 0, 1 to negative 1, and it is parallel to vector v, which is 1, 5, and 6. Example, very well. describe C, which is a set of points such that x is equal to cosine t, y is equal to sine t, and z is equal to t. Okay, perfect. So my x is cosine t, my y is sine t. Remember that when we talked about parametrization of functions, we say that one of the famous and important parametrization is using sine and cosine. So recall that when we have x squared plus y squared equals to, for example, a squared 1, we have equation of a circle in 2D. But this equation in 3D is not a circle. This equation in 3D is a cylinder. So here you have x squared plus y squared equals to a squared. So the center is at the origin. X-axis, here we have y-axis, and here we have z-axis. Well, a and a. So here you have a circle. And then, so the projection of cylinder on xy plane is a circle. But this continues. You have circles built on top of each other, and it forms a cylinder. It's parallel to z-axis. Very well. So we know this information. We have seen this before, the parametrization before, the equation of a cylinder before. What about this vector valued function? This vector function says, hey, my x is equal to cosine t, and my y is equal to sine t. X squared plus y squared is equal to cosine squared t plus sine squared t, which we all know is equal to 1. So what do we have? We have a unit circle in xy plane. Unit circle in xy plane. But here we have z equals to t. It means that our z is changing as well. There you go. So here you have x-axis, here you have your y-axis, and here you have your z-axis. For example, if t is equal to 0, when t is 0, our vector function is going to be cosine of 0, sine of 0, and t, which is equal to 0. So it is equal to 1, 0, and 0. 1, 0, and 0. If we plug in different values for t, we can actually follow the position of this particle. So as you mentioned, here we have the behavior. Just graph it a little bit better. This particle starts at this point, for example, and start moving around counterclockwise. So in a cylindrical format. This is actually a helix. And continues and so. So this example says, find a vector equation. So far we describe the vector function. Now we're going to write the vector equation. Find the vector equation for the line segment, that passes through these 2 points, that joins these 2 points, joins P, 1, 3, -1, and Q, 2, -1, and 3. So we have 2 points in the space, and we want to write down the equation of line segment. Recall that the equation, vector equation, of line segment is written this way: R of t is equal to 1 minus t times R sub 0 plus t times R sub. Okay, we have 2 points. We can actually form R sub 0, the first vector, and R sub 1, the second vector. These vectors are actually connecting the origin to these 2 points. So R of t is equal to 1 minus t vector R sub 0. So we're going to use vector symbol 1, 3, -1 plus t times R sub 1, which is the terminal point, the terminal vector, vector symbol 2, -1, and 3. The rest is algebra. We distribute 1 minus t, we distribute t, and then we combine corresponding components. So R of t can be written as 1 minus t, comma, 3 times 1 minus t, comma, -1 times 1 minus t, plus 2t minus t and 3t. Well, if we combine these, we get 2t, 1 minus t, which is t plus 1, comma, -t minus 3t, -4t plus 3. And finally, 3t plus t, 4t minus 1. Okay, our last example in this section says, find a vector function that represents the curve, What is that curve? The curve of intersection of a cylinder x squared plus y squared equals to 1, and the plane y plus z equals to 2. Okay, perfect. So what are we doing? We are just finding the equation of a curve, the vector function that represents the curve. What is that curve? Here you have a cylinder, and you're slicing that cylinder with a plane. So the intersection between them is equal to a curve we want to find that equation. To find the equation of the intersection between the cylinder. So again, x squared plus y squared equals to 1 is a cylinder in the space. X squared plus y squared equals to 1. And the plane y plus z equals to 2. We use parametric representations. Okay, we already know that if you have x squared plus y squared equals to 1, x can be written as cosine t, y can be written as sine t. Note that your r radius is equal to 1. So if you write it in general form, r cosine theta, r sine theta, since you have a unit circle as a reflection of your cylinder in xy plane, r is equal to 1. So x is cosine t, y is sine t, and this cylinder has it's parallel to z-axis. So z is equal to t. Let's set t equal to 0 to make sure that you're working with this cylinder in xy plane. So when z is equal to 0, it means that we're just looking at this flatted cylinder in xy plane. This is simple. Cosine t, sine t, and z is equal to 0. Well, this plane gives us z in the space. So since z is equal to 2 minus y, and we know that y is equal to sine t, our z is equal to 2 minus sine t. The intersection between this cylinder and this plane in the space. So our function is f of t, which is our x, cosine t, and y equals to sine t, and z is equal to 2 minus sine t. And note that your t is bounded between 0 to 2 pi. You only have one intersection. It doesn't rotate around. That's why you restrict t between 0 and 2 pi.